The observable universe is the portion of the cosmos we can examine through telescopes and other scientific instruments. However, our observations are limited by the speed of light, the ultimate cosmic speed limit, because light takes time to travel. We can only see objects whose light has had enough time to reach us. This means vast regions of the universe may remain hidden from view, not because they don't exist, but because their light hasn't yet arrived. As a result, the observable universe represents both a vast field for discovery and a natural boundary of our current knowledge. Estimates suggest the observable universe spans about 93 billion light-years in diameter, which might seem counterintuitive, considering the universe is only about 13.8 billion years old. This discrepancy is explained by the expansion of space itself. As the universe stretches, distances between celestial objects grow, so light emitted billions of years ago has had more time and space to travel, allowing us to observe areas much further away than might initially seem possible. Despite its inherent limitations, the observable universe remains a treasure trove for scientific exploration, and our understanding continues to deepen with advances in technology and space-based observation. Modern instruments have dramatically enhanced our ability to study the universe's structure, composition, and history. They provide crucial data on events that occurred billions of years ago, offering insights into the formation and evolution of galaxies, stars, and other cosmic structures. One of the most powerful tools in this effort is the ability to detect faint infrared light from the earliest galaxies, which lets scientists peer back to just a few 100 million years after the Big Bang. This allows us to see the universe in its infancy. A key phenomenon enabling this kind of observation is called redshift. As galaxies move away from us due to the expansion of the universe, the light they emit is stretched into longer, redder wavelengths. Instruments sensitive to these wavelengths allow astronomers to study extremely distant galaxies, ones that formed when the universe was still very young. These observations have revealed vital information about the early rate of star formation and the processes that gave rise to the first galaxies. Understanding how stars ignited and galaxies evolved in those early epochs is central to building accurate models of cosmic evolution. Yet, beyond mapping galaxies and examining ancient light, the question of whether life exists elsewhere in the universe remains one of the most compelling drivers of modern astronomy. For centuries, humans have speculated about extraterrestrial life. In recent years, the discovery of thousands of exoplanets, planets orbiting stars outside our solar system, has made the idea increasingly plausible. Using techniques such as transit observations and radial velocity measurements, astronomers have identified many of these distant worlds. Some share characteristics with Earth and orbit within their stars, habitable zones, regions where conditions might support liquid water. One intriguing discovery involves the detection of water vapor in the atmosphere of an exoplanet named WASP-96b. While this planet is not considered Earth-like, the presence of water vapor clouds and haze was unexpected and significant. It challenges current assumptions about what types of planets might be able to support life, or at least the ingredients necessary for it. Water is one of the most crucial factors in assessing a planet's potential habitability. Discovering it in such an unlikely place suggests that life-supporting conditions may be more widespread than previously imagined. Yet, even as we uncover more about what's within our observational reach, questions about what lies beyond continue to intrigue scientists. By definition, the observable universe is limited by the distance light has traveled since the Big Bang, but many cosmologists believe the actual universe extends far beyond this boundary. Some estimates propose that the total universe could be at least 1,023 times larger than what we can see. This staggering scale highlights how much remains out of reach and open to speculation. One of the most fascinating ideas to arise from this speculation is the concept of the multiverse, the possibility that our universe is just one of many. Some interpretations of quantum physics, particularly the many worlds interpretation, support this notion. In that view, every possible outcome of a quantum event actually happens, each in its own separate universe. Though still highly theoretical and lacking direct evidence, the multiverse hypothesis has captivated both scientists and philosophers. Some believe it could explain why the physical constants of our universe appear finely tuned for the existence of life, while others caution that such theories, though elegant, may be untestable with current technology. Another puzzling phenomenon that may hint at something beyond the observable universe is known as dark flow. First proposed in 2008, dark flow refers to galaxy clusters moving in a uniform direction at speeds that current models of matter distribution struggle to explain. This motion could be the result of a massive gravitational influence from a structure outside our observable region. Some researchers think dark matter or dark energy may be involved, though both remain poorly understood. Dark matter and dark energy don't emit light, making them nearly impossible to observe directly. Yet together they are believed to comprise most of the universe's mass and energy. Dark matter helps explain the behavior of galaxies under gravity, while dark energy is thought to be responsible for the universe's accelerating expansion. The ongoing study of dark flow seeks to determine whether these invisible forces can account for the mysterious movement of galaxy clusters, but the scientific community remains divided. Some findings support the idea, while others suggest that what we're seeing could be due to data interpretation errors. Regardless of the outcome, dark flow underscores how much we still have to learn about the cosmos. The search for answers leads scientists to tackle increasingly complex and profound questions, from the birth of galaxies to the fate of the universe. This quest doesn't just involve collecting data on stars and planets. It's an attempt to piece together a grand cosmic narrative in which humanity plays only a small but growingly self-aware role. One particularly intriguing area of inquiry is the geometry of the universe. Current observations suggest the universe is flat, meaning parallel lines remain equidistant even across cosmic distances. This flatness is supported by data from the cosmic microwave background radiation, the faint afterglow of the Big Bang, as measured by missions such as WMAP and Planck. A flat universe implies that it will continue to expand indefinitely, although the rate could change depending on how dark energy behaves over time. Even this seemingly simple observation opens new doors. Is the universe flat only within the observable region, or does its shape change beyond what we can see? If it does curve, what might that mean for the universe's ultimate fate? The cosmic microwave background (CMB) is one of our most valuable tools in exploring these questions. This radiation offers a glimpse of the universe as it was just 380,000 years after the Big Bang. Tiny variations in its temperature reveal clues about the distribution of matter, the rate of early expansion, and the seeds of galaxy formation. These patterns help scientists trace the universe's early development, but they also raise deeper questions about what came before. One of the most mysterious periods is cosmic inflation, a rapid expansion that occurred in the first moments after the Big Bang. If we could detect remnants from this era, such as gravitational waves, we might uncover insights that go beyond the observable universe itself. The theory of eternal inflation builds on this idea, suggesting that some regions of space continue to inflate while others, like ours, stabilize and evolve into isolated pockets. This concept feeds directly into multiverse theories, proposing not just multiple universes, but an endless variety, each with unique physical laws. Though such theories remain unproven and may never be testable, they continue to drive theoretical research and philosophical debate. Meanwhile, observational astronomy is achieving extraordinary milestones. With advancements in technology, scientists can now peer deeper into space and further back in time than ever before. Infrared observation tools are particularly powerful because they can penetrate clouds of cosmic dust and reveal early stages of star and galaxy formation. Recent findings have shown massive, well-structured galaxies that existed just a few 100 million years after the Big Bang, far earlier than current models predicted. This challenges our understanding of how quickly matter formed complex systems, suggesting either unknown mechanisms were at play or our models, particularly regarding dark matter, need to be revised. These unexpected results illustrate the self-correcting nature of science. When reality contradicts theory, scientists must reassess assumptions and develop better explanations. For instance, it's possible that star formation in the early universe was far more efficient than expected, with dense clouds of gas collapsing rapidly under gravity. Alternatively, interactions involving dark matter or other unknown processes may have accelerated the formation of cosmic structures. Understanding the universe's ultimate fate is closely linked to its early development. A key part of that puzzle is dark energy, which is believed to drive the accelerated expansion of the cosmos and currently accounts for roughly 68% of its total energy content.